feel free to raise your hand anytime in the middle, ask a question, disagree also, it's good. All right, so I'm going to start with some of the challenges I see on my radar screen as really worth deserving attention to improve our ability to have impact in the world using GFlowNets and derivatives that I'm thinking about. So, as you know, if you've played with GFlowNets, in fact, if you play with RL in general, that we can train these systems, these generative policies, when the objects that we are constructing, the number of steps that are involved is small enough, like 100-ish number of steps, more or less, is what we can do reasonably well. If we multiply by 10, yeah, credit assignment becomes a problem, or something else. That's our guess. Credit assignment is a problem. And I'll talk about later of applications where I'd like to use GFlowNets in a way similar to what Tristan, I assume, talked about regarding generating theories of the world, like causal graphs and causal parameters, where the theory is just way too big for the current algorithms that we have. It's not going to be something we can generate in one shot. And so to expand the scope of application of these methods, I think it's really worth first understanding, is it really a credit assignment issue? And maybe we can learn from what people in RL have been doing. Or is it something else? There's another practical reason why having more than a few hundred steps is not great, because each step is running a neural net, producing an output. So for most reasonable tasks, you want to limit that. If it's, so it's just computational time. Now there's a path which I'm not sure if this has been covered in the workshop. Sorry, I wasn't there all the time. I guess maybe in the continuous things, there's a way to generate a big object, which is not like the molecule generation one little bit at a time, given the previous ones, or like autoregressive LLMs and so on, but generate everything in one shot badly and then modify it, and then modify it, and then modify it, like in MCMC, for example. And in principle, you could generate much bigger objects in this way. So, by the way, there's a computational reason for doing it this way. So imagine you want to generate a parameter vector, like if you're Bayesian, and you got 100 million parameters. You don't want to do 100 million feed-forward steps on a neural net, right? It's not, even besides the credit assignment problem, it's just not reasonable. But you can certainly generate a vector of size 100 million. I think that's something computers today can do. And then modified 100 times. Right? So now that becomes something, because GPUs parallelize. We can have a lot of outputs, but we can't really run sequentially 100 times or 1,000 or 1,000,000 times. That's going to be too much. So there is some ongoing work that's like that. It's the same style of computation you find in diffusion, denoising, and things like that, and in MCMC. I think we need to push that boundary and see how far we can go with that, and really try to scale it up. There's another less clear thread that will come back in another slide. Something that's been explored a lot in reinforcement learning, which maybe we can also learn from. That's called hierarchical reinforcement learning. So okay, we can't generate a huge object, easily. So now it's back to the credit assignment. But maybe we can like break down the problem into smaller problems, kind of divide and conquer. So people in hierarchical RL think about options and skills and, you know, a high level plan. So we decompose the problem into reusable pieces. So I think this is really worth thinking about. And I'll come back to that. The other big area, which I think is worth spending more time on, is training efficiency. And the tricks we're currently using now, we kind of figured out pretty quickly in the first few months of playing with GflowNets. And there's been a lot of work trying to improve on that. And I think we only made marginal improvements. So there may be several aspects to this, but one that I find particularly mind-boggling is also something that we can take inspiration from the work in reinforcement learning exploration. So, you know, in RL, we're asking, where should the agent go in order to collect useful information, given that it can't go everywhere? Information that will help it later to get high rewards. And so in the case of GflowNets, we have this freedom of choosing the training distribution, the behavior distribution, the behavior policy. How do we pick those training trajectories? So we have tricks. We can use some data. We can use greedy exploration, tempering, prioritize replay, maybe others I didn't think of. But I think there's a lot of potential there. Or maybe it's like very hard, and I don't know. But it could really help to scale up. Because sometimes, if you've played the GflowNets, we think we have a well-defined problem. We, turn the crank, and the optimization doesn't work. Like we're stuck in suboptimal solutions. We don't find the high reward configurations, trajectories, and so on. So it's an optimization problem, and it's an optimization problem in the case of GflowNets, which we can think of as an exploration problem. So when we think about it as an exploration problem, my geometric intuition is that a lot of it is about generalization. So if you think about what we're trying to do is guess where potentially good modes, like high reward regions, would be without having to try everything. It's the exploration problem, right? Where is there high reward in a very high dimensional space? And it's hopeless if you just do like some local search. I mean, we should do it. And there's some nice recent work combining MCMC local search with GflowNets, for example, but it doesn't solve like the bigger problem. And so maybe the solution isn't going to be with the auto loop or the tricks, generic tricks. Maybe the solution is going to be, as usual in machine learning, how do we get better generalization? Inductive biases, right? So we kind of do something magical with the architecture. We invent attention, and suddenly you got a revolution on your hand. So that's one thing that I think is worth pushing. Maybe exploiting the particulars of the task, or fairly general ideas like I was talking about, notions of abstraction and reusable components and things like that. So which is all about generalization. Like how do we're trying to guess modes from a few modes. So it's a difficult generalization problem. So the other source of information, which I think Jared, who talked yesterday, explored, but we haven't found yet a satisfying solution. I think he has a paper, but it's exploiting the uncertainty about what the neural net has learned. So if, we're trying to get the loss low everywhere, and there may be regions where the neural net can generalize with confidence that, okay, this should be low reward place or this should be a high reward place. Mostly we need to explore in regions of low certainty, where, in other words, like if you were Bayesian, you would like to go. So we may want to think about the training problem in GFlowNets like an active learning problem, because we're able to query the reward function. It's not like a usual learning problem with a fixed data set, and we're trying to minimize the loss on those points. It's very different. It's much more like an active learning problem. And maybe we should be thinking about training methods for GFlowNets that are inspired by the ideas in active learning. And one of the central ideas, maybe Mark presented, is estimating uncertainty and then direct your attention to the places of high uncertainty. So how to do that isn't trivial. Like simple things we've tried, it's not that easy. And then one reason why it's not trivial is that the uncertainty that the neural net has about some particular configuration is going to change the moment you update it with some example, right? So you can't have like a separate process that estimates uncertainty. We tried things like this with Salem and others last year. It's got to be something built in your GFlowNet that it both estimates flows, policies, and their uncertainty, so that you don't have this like non-stationary issue that otherwise you would get. Okay. Any question up to now? Because I'm going to kind of change sort of mood a little bit.
Yoshua, there's so you're talking about the uncertainty in the policy, right?
Sorry?
You're talking about the uncertainty in the policies, right?
Yes, ultimately it's the
in
uncertainty in the policy or the flows or whatever your parameterization is. Yeah.
Because you could also leverage the uncertainty in the reward, or are you assuming the reward is perfect? Is
No, so here I'm assuming the reward is known. Okay. So this is a different question. Like if you're also learning the reward function, and that's the usual active learning, Bayesian optimization, GFlowNet style thing. But now I'm talking about a different thing where we want to improve training of the GFlowNet, and we want uncertainty about what the GFlowNet has learned.
So I have a question about the generalization.
Did you get closer to the microphone or speak louder?
Yeah, so I have a question about the generalization part. Do you think it's related to picking the training trajectories, or it's more related to choosing the state space and action space of your GFlowNet that will help you generalize? Because maybe there is some
and the architecture. So in the GFlowNet community, we tend to think, oh, okay, so we have all of this GFlowNet machinery and plug in your architecture and don't worry about it. But I'm saying, well, maybe it does matter.
I mean, not only the architecture, but even the state space.
Yeah, the state space, the action space, all of this is, involves choices that could have a huge effect on how easy or hard it's going to be to optimize our objective. Yeah. By the way, it's the normal thing in machine learning.
I was just going to comment about the uncertainty estimation, that somehow the information we have about the forward trajectories and the forward policy and the backward policy and how inconsistent they are with each other, that's already some kind of built-in to estimate uncertainties. So I'm wondering.
But they could be consistent and uncertain.
True. Then you go,
So
yeah.
I think what you're saying is like an extra clue, but it's not sufficient.
No, it's not. I just wanted to comment.
Okay, so let me move on. I'm gonna now talk about Bayesian stuff. before I talk about Bayesian stuff, I'm going to talk about the problem with not being Bayesian. By the way, before GFlowNets came into like my mental landscape, I used to think that Bayesian machine learning was nice in theory, but impossible in practice. And I've changed my mind. And so much so that now people think I'm a Bayesian. I've always been, it's just I thought, oh, this is like, oh, nice, thank you. But yeah, I didn't see how we could mesh that with neural nets and what, you know. But now I see, and we have several papers going in that direction. So yeah, what's the problem with maximum likelihood? In practice, we you know, with LLMs, for example, we get hallucinations. We get our trained models to be confidently wrong, and that's bad, really bad, and potentially really dangerous. And when we consider a model that is then being used as like a reward function, or in reinforcement learning as a world model, and then we're going to optimize some policy on that, then things get even worse, because the policy is going to optimize over that confidently wrong model, and it's going to be sure that it has found a way to make a lot of money, but it's going to be a fantasy. And yeah, when it's too good to be true, don't trust it. So what can we do about this? I'm going to try to argue that we can be Bayesian, and that GFlowNet style methods can help us deal with that. And then later I'll talk about some of the challenges which are related to what I already introduced. Okay, so again, why being Bayesian is important, and I'm going to highlight the safety aspect of it. And safety introduces the aspect that some of the actions that your AI system can take can have catastrophic outcomes. How do you avoid that? So you have to be conservative in some way. And if you're going to be conservative, you need to have a notion of what can go wrong, even if you're not sure. Okay, so let's consider this like really simple scenario. You got an AI. It's in front of two doors, left door, right door. You have to choose. Go left, go right, binary. And it's seen data. Based on that data, there are two theories that are compatible with the data that it could choose. And if it's going to do maximum likelihood, it's basically going to pick one of them completely arbitrarily. So if you think about neural nets, depending on how you initialize it, or the particular biases that exist in a model, but usually, you might find one theory or the other theory. By the way, one way of being Bayesian in a cheap way is to train multiple neural nets with different initial weights, and then that gives you a sort of cheap Bayesian solution. But let's see here. Our robot can go left or right. And the first theory, so, in the bubbles there, the theory on the left says, if you go left, you die. That's the catastrophic outcome. If you go right, you get some cake. The other theory says, if you go left, you get some cake. If you go right, nothing good, nothing bad. Okay, so what happens if you pick one of the theories, maximum likelihood? We don't know which one is correct. So let's say it's 50%. And if you're not lucky, you pick the wrong one. So that's 25%. So let's say that the correct one is the one where you die if you go left, and you pick the wrong one. Well, you die because you think you can get cake and you're going to die. So not good. If you're Bayesian, the idea of being Bayesian, all this math, it just sounds complicated, but really it's super simple. It's just keep track of all the theories and act accordingly in a rational way. So keep track of the theories. You just by inspection, you can say, "Ooh, I don't want to go left just in case," right? Go right. So that's it. And you don't die. You get 50% cake, 50% nothing. Pretty good. All right. So that's easy when you have only 2 theories. But what if you got an exponential number of theories? And how do you do that, in a non-toy setting? So if I say that a theory is a neural net, it sounds like it's not feasible unless there's just 10 theories. But if there's an exponential number of theories, because there are many combinations of things that could be, right and wrong, maintaining a billion neural nets is not going to cut it practically. So how could you do that? In the past, people have been handling the Bayesian machine learning question, making abusive assumptions which in the end mean that those systems didn't scale to complicated tasks. So making very strong assumptions about the underlying distribution that make it possible to do the Bayesian calculations. There's going to be like sums and integrals that are intractable in general, but sometimes you can do it analytically, and like linear regression, for example. But of course, then things are not linear, and then your model doesn't work. Right. So here's an important message. Even though the exact Bayesian posterior is generally intractable, in principle, we could use a neural net to represent the distribution over those theories. Right? So instead of maintaining a billion theories, let's say you've got one neural net that is not representing a theory, but it's a generative model that if you sample from it, gives you a theory. Okay, so you don't actually enumerate the theories, you just have a machine that can sample one of the theories. And I'm gonna try to explain that if you had a GflowNet that would do that, you can basically solve the problem. But there's something interesting here. If you've kept track of all the excitement in AI in the last few months and years, we can train really, really large neural nets, and they can learn really, really complicated distributions, right? This is the whole point about the LLMs and frontier AI systems. And in fact, if you look at the GflowNet objectives, with enough compute, like a large enough neural net, and training long enough, you can get arbitrarily close to an objective value of 0. I mean, earlier I said it's hard to train and so on, but it's just a matter of how much compute. It's not about generalization. I mean, generalization will allow you to train faster, but in principle, it's just a matter of compute. And so, maybe there's a way that we can actually approximate these posteriors that are intractable. In fact, every day we use neural nets in many applications to compute distributions that are otherwise, intractable. We approximate them, right? So it's just saying the same thing. Okay, so how would you do that? Right, so remember that the GflowNets learn a generative model over some objects. So here the objects would be the theories that the agent has in its mind. And it could sample one of those theories one at a time. And the objective functions and, the training objectives, we have many, but bottom line, they all have the property that if you minimize them, then the GflowNet will sample proportionally to the reward function. So how could we use that to get a Bayesian posterior? Well, it's very, very simple and easy. It's just one line in the bottom. So let's say we want to get, what is the Bayesian posterior we want? We want two things, but the main one is P of theory given data. So theory is like a hypothesis about how the world works, or something, you know, a model, whatever. Could be parameters, but it doesn't have to be. Could be a program. That's the way I like to think about it. So we would like to have a neural net that samples a program that's a theory that explains your data. And we'd like to pick the theory that is the most likely. No, we don't want that. We want to sample a theory proportionally to its posterior. Okay, so that's what we would like. And if you remember Bayes' rule, which hopefully you do, in order to get a sample from that posterior, we can use as a reward function the thing on the left, which is the prior P of theta times the likelihood P of theta given theory. And the reward is actually something that we can compute. So the prior might be something like 2 to the minus length of the theory. We can choose priors in many ways, but that's just one has a lot of nice theoretical properties. Anyway, it's easy to compute. The likelihood is like your normal, like maximum likelihood objective, right? You would have log likelihood usually. So it's something we can compute, and we can even easily show that you can get away with using a mini batch of data rather than looking at the whole data set, because data here is the whole data set. If your data set has a billion things, well, you know, you don't want to have to do a pass for each update of your GFlowNet. You don't want to have to do a billion computation, you know, or at least you know, a billion examples. But it turns out it's fairly easy to get a stochastic version of the reward using a mini batch detail. But point is, in principle, we can train GFlowNets so that they will sample over these theories. If the theories are small enough, right? Because remember what I said at the beginning. Now, actually, what you want is a little bit more than that, but it turns out GFlowNets can do that for you. We want two things. We want to sample over theories. So that's P of theory given data. Here, data is D, sorry. But like, what do I do with a theory? Actually, what you want in practice for many problems is answering a question, also known as inference. So let's say, think about an LLM, like X is the question and Y is the answer. So what you want is P of, you want another neural net that learns to sample answers Y, given questions X, and given the data set. That's the thing you want. That, you know, you've got a data set, somebody asks you a question, and you want the answer. That's like the rational question that you really are after. And you see that you can write it as the, you know, marginalization, where you sum over all the theories. Well, that's where the other guy that samples theories becomes useful. Now, if I had to run, you know, to estimate that sum by Monte Carlo, by sampling from the other network that generates theories and then cranking, it wouldn't really work. I mean, it would be very expensive, because at runtime, you would have to call this, and it would be a pain. So there is another way, which is we jointly learn to sample and to marginalize. So we can like train one GFlowNets that does two things at the same time. And if you followed my little presentation yesterday morning, I showed how you can do that. If you think about the initial state flow, or which is the Z, or the partition function, it is an intractable sum just like this. And so, you know, we train the GFlowNet, we get both the marginalization function and we get the sampler of theta. So in terms of like the mathematical principles, we know how to do that, both of these operations. The only little problem is theta is way too big for for most problems of interest. Okay. Now,
sorry.
Yeah. Go ahead.
So for your second length, for marginalization, your P of theta not only depends on D, but it
Yeah.
depends on your new input. So does that mean you need to train a GFlowNet for every input for every new input that you want to feed?
No, you could condition on X.
You can condition on.
So I didn't do all the details, but instead of the one, so think of D as a set of XY pairs. Actually, what you need is you condition on that plus an extra X.
Yeah.
And you can get it. There's like a simple way to get both. Okay. Yeah, don't worry about it. All right. So, as some of you know, I've been worried about misuse of AI and loss of control of AI this year. And I've been thinking a lot about, from a technical AI point of view, what can we do? And I've come to the conclusion that what would be really great to make sure we can build AI that are not dangerous is if we could train an AI that understands the world and human psychology well enough, but also understands its own limitations of knowledge, epistemic uncertainty. So in other words, is Bayesian. And anytime a machine like an AI, another AI, or maybe proposes to perform an action, we would call this, which I call an AI scientists, because it's basically a world model. So it has, sorry, what's going on? You know, it can do these marginalizations, so it can answer questions about harm that may follow given a particular action in a particular state. And so, yeah, if we were able to train such a specialized AI, well, in general, it wouldn't be specialized. It would be knowing a lot of stuff in order to be able to answer these questions. We could use it to reject actions that are not safe. And by the way, that's very different from the way people are thinking about safety these days. And more reassuring, because I'm not reassured by the way people are doing it right now. They're like spot checking. Okay, let's try this. Let's see if the AI, gives a recipe for building a bomb to bad guys. All right, but there's so many ways you could query these systems. It's hard to be sure that nothing bad will happen. And in fact, as soon as these LLMs are put out, somebody finds a way to destroy all the safety protections. But if we had this Bayesian thing, we could get quantitative, probabilistic safety guarantees, which I think would be a lot safer the day when we reach machines that are smarter than us. I wouldn't trust just some kind of, oh, let's try it and see if it works. I would rather have some sort of guarantees that it's not going to turn against people. Okay. So now let me go back to this question of training an AI scientist. As I said, in principle, we have the math for it. We just don't have the algorithms to scale at that level of understanding of the world, comparable to what you find in ChatGPT and things like this. So what could we do? Well, I want to go back to this question of breaking the task of training and building an understanding of the world into smaller pieces, like this divide and conquer. So I've always had huge inspiration in my career from human intelligence. It's been an amazing success. How do humans manage very complicated theories of how the world works? Do we spit out in our mind a theory of everything? No. We have little pieces that are relevant to the current situation or some imagined contexts. And somehow it's like a patchwork of how the world works that is more or less consistent. That if we think a lot about all of these things, we managed to. So think about all the papers that scientists write. They're like, each of them is talking about a little piece of reality, theories about things, and evidence that it might be a good theory, a piece of theory, right? So yeah, so I think this is a direction I'd like to explore. There's another analogy that I find inspiring, which is how we do programming and how we do mathematics. And there are a lot of connections here. So programming, mathematics, scientific theories. Presumably, you know, we kind of done all of three here, people in this room. They all have this patchwork kind of property, but also they all also have this notion that we can define little pieces, like a definition of a function in programming, or a lemma in mathematics, that can be reused in many ways in order to come up, if we were to unfold it completely, with a theory that's fairly small, but explains a lot of things, which is, remember, Occam's razor and like machine learning 101. So, yeah, I think that solving this problem might give us answers to building AI for science, for mathematics, for programming. They're all connected in a deep way, right? I don't want to, yeah. So the last bit I want to mention about safety, if we were to apply these ideas, I mean, if we were to come up with algorithms that would do all these things. So going back to the safety question, current approaches to building frontier AI systems rely on reinforcement learning, and there's a fundamental like issue that I mentioned, you know, too good to be true, and we're optimizing these systems so that they might find fantasy answers. And in fact, there's a lot of analysis suggesting that as we increase the compute power, as we make these neural nets bigger, as we train them longer, we get less and less safety. And so that's why a lot of people right now are trying to figure out, you know, do they know how to do X? Because if they do, then that's maybe dangerous. And even there are methods called unlearning, where, okay, so we've trained an LLM, but it knows how to make bombs. Can we like remove that from its knowledge? So all sorts of like ways to address the safety problem. But it would be nice if instead we were in a scenario where the more compute we put in our neural net, the longer we train it, the bigger we make it, the safer we get. And I have this conjecture that, you know, under some hypothesis, the sort of approach that I've talked about, if we can find efficient algorithms that can scale, would have exactly this probability. Because the more we would train our neural net, maybe GFlowNet style, the more it would approach the Bayesian posterior. And the Bayesian posterior would be sort of safe by construction. Because when it doesn't know if something could be harmful, you know, it would basically not do that action. It would say, well, you know, there's a chance this could be harmful, so let's not do it. Yeah, I think I'll stop here.
Yoshua. So this is not well phrased, but I want to discuss the non-stationarity of that distribution of human preferences.
Oh, yeah. Oh, you
that-
mean in time?
Yeah, I mean, we
Yeah,
change.
yeah. It's
So-
it's a big goal, right? We can start with trying to understand a single human, but ultimately, for an AI to be safe, it has to build a model possibly very uncertain, where it knows its own uncertainty about all humans, or at least all humans that could be, benefiting or harmed by its actions. So it's a tall order, but in a way we are doing it, right? So I don't know what most of you think, but I have some general idea, and including some uncertainty, because I know that there are variations between people, and when I get to know a person, I know what their preferences are. And when we're not sure because we don't know that person, we behave accordingly, right? This is what we would expect from a Bayesian AI.
Yeah, this is actually the connection to the second thought, which is we're going to have also to decide how much detail we want to give that AI. Like, if it's going to have an impact on me as an individual, then I guess, as you just said, you're going to have to provide information if you want about yourself. But if you're going to have, if this is going to be if the action of the agent that's querying the scientist is going to be more global, then you have to have a representation of that society or that group.
Yeah. The only way eventually, when we reach AI that are deployed in the world, is that they have a pretty good understanding of society, psychology, and all the diversity of cultures and people. Yes, there's no other way around.
I'm also curious about this question of building the Bayesian posterior of human preferences. And it seems to me that in general, in Bayesian, when we do Bayesian inference, we treat data points kind of similarly. But when I'm thinking
that's a choice we can make.
Yeah, okay. But I'm curious in this specific situation, because maybe for some questions in general, you may need some expert knowledge to estimate the harm, let's say, of some action.
Yes.
And very few maybe people in the world can give you precise answer, and
Right.
the general population would not know. So I'm curious how we're going to treat these situations.
Okay, so one thing I didn't talk about is, in order for the kind of approach I mentioned to work and to provide any kind of guarantee, it will need to have figured out pretty much all the ways that humans theorize about themselves and about how the world works, and moral questions. So yeah, I'm not saying this is something we can build tomorrow, but if you think right now we're trying to figure out the algorithms that could lead us there, and we could start small. But yeah, ultimately, if we want to build AI systems that are very powerful and maybe smarter than humans, we want to really make sure that they're going to behave in a way that is consistent with all of the information available to the human. And by the way, if it doesn't know, but it thinks some humans might have useful answers, then it could go and ask them. In fact, one of the original works coming up with similar ideas is in Stuart Russell's book, 2019, Human Compatible. And there, the focus he puts, and in Europe's paper they had in 2016 on this, is the relationship between the human and the AI. So when the AI doesn't know, because it's Bayesian, it has uncertainty, it can ask the human, what do you think about this? Or, would you consider this bad? Yeah.
Thank you.
So the uncertainty is also useful from an active learning perspective for the AI. If it doesn't know if something is harmful, then it might try to acquire that information in a safe way, right? We don't want it to start dissecting humans just to see what's inside.
Yeah, maybe a small follow-up. What do you do in the situation of conflict when some people think it is good, other people think it is...
Sorry, can you speak louder?
Yeah, so small follow-up. What do you do, what this system will do in the situation of conflict when some people think that this is harmful?
You mean disagreement?
Yeah, disagreement between people, what AI agent would do.
Well, so disagreement in a Bayesian framework is the norm. It's not the exception. We've got many theories and they're not compatible everywhere. So there's some questions on which I think we should go left and you think you should go right. And the rational way of dealing with this is to consider all the theories weighted by how much they are compatible with the data. So basically, we just keep the theories that are consistent with everything we know. That prunes out a lot of garbage, but there's still a lot of theories. And then we just average out their answers. If we want to take a decision, we can also, if you want, do something like measure their variance, and that's going to tell us something about uncertainty. So that's exactly what Bayesian is good for, dealing with disagreement, because we don't know what is the right answer. And we have to have what's called epistemic humility.
But what we do, in the end.
It's like, what's democracy? I mean, ideal democracy is somehow we come to the agreement that most people agree with. I mean, that the decision that most people agree with, or something of that kind. It's the same idea. Bayesian machine learning, is to social decision making like democracy.
Makes sense. Thank you.
Yeah, that made me think. But I actually had a question about the part about partial theories. So I fully agree with the idea that brains or humans do not instantiate like a theory of everything, and but I still don't fully grasp what you mean exactly by a partial theory, and especially you had
think about a paper.
So I get the idea, but for example, you say we need to be able to evaluate the partial theories. I think you have something like this. So what exactly you mean by this? By how do we what is what we need that we don't yet have partial theories?
So again, think about scientific papers. What do we need to evaluate a paper? We don't need to look at all the data collected by all humans since the beginning of time. We just need to look at some particular experimental data that helps answer questions about what the hypotheses are being tested in that paper or something, right? So we somehow have ways to focus the match between theory and data to a very small part of the data space in terms of which variables we look at and what we do with that. And I can come up with heuristics to do this, but I would like to have a mathematical framework that naturally does that. That will that will select just the data and maybe even a random subset of it, because you probably can't check everything. So think about a theory like theory of gravitation. Well, you're not going to collect every single thing where gravity comes about. You want to just collect enough to get statistical confidence. So I think we can really take a lot of inspiration from how humans solve the science discovery problem in order to inspire our algorithms. But I don't know how to do it.
Yeah, I get that. So it's still, if I may follow up, so I guess mathematically, like a partial theory would be like a subset of variables from the data, right? So I have struggled seeing how can we come up with a general way of evaluating arbitrary subsets of theories, the combination of the combinations of partial theories, the diversity of partial theories that we could have is huge.
Right. So the way I like to think of building blocks for theories is similar to the building blocks for programs and for mathematics. I call them statements. So you've got a short statement, and these statements are not independent of each other. They might refer to the same objects, the same entities, the same definitions. And each statement can be true or false. And a partial theory is just going to be a collection of these statements, which help you explain particular aspects of some particular data points. So partial theory is only helping us understand some projection of the data in some directions that we care about. So a theory usually in science is about some learned projection of the data, like some functions of the data. Like, let's say I get an image, but really what I care about are, okay, where are the objects, where they are, maybe I care not only about position and not velocity, whatever, right? So we project the high dimensional raw data into some particular variables that are relevant to the theory. And then the theory is checking whether it's consistent with the values that these variables took. Yeah.
So could you elaborate on how GFlowNet might help with learning a world model?
A world model?
Yeah.
Yes.
So would you see that more at the level of one GFlowNet where each sample might represent, one piece of the world model, or would you see it at the level of multiple GFlowNet that are, trained to learn parts of this world model?
Okay, so maybe one way to think about this, did you guys see the forward-looking GFlowNet? No, okay. No, I don't have it in my slides. But so in a normal GFlowNet, you have to go to the end of generating the whole theory before you get a reward. And that's not going to fly, right? That's what I've been talking about. And we've motivated by this notion of partial theory and so on. In fact, for more than a year, I've been thinking about this. We explored a few things. One of the things was, can we train a GFlowNet even if we don't get to a terminal state? So it's just one GFlowNet, but it's going to initially pick some aspects, some variables. Let's say that what the GFlowNet does is it picks a bunch of statements. So let's say a theory is a bunch of statements that are true. The full theory is generating all the true statements that are sufficient to explain the data you have. But that's going to take too much time. So the GFlowNet might only evaluate a sub-trajectory that considers a small number of statements. And maybe something different from the GFlowNet that's more like exploratory policy chooses which statements are relevant to some data we're seeing. So if I see something, I might invoke just a little partial theory that's relevant to that, for example. In the real life, that's what happens, right? We see a movie and, things come in our mind that are relevant to what we're seeing.
But so that requires to have some sort of feedback in the, middle states and not necessarily at the terminal.
Right. So in the forward-looking thing, we assume that the reward function isn't like a black hole, isn't a sort of homogeneous thing, but it can be broken down into smaller pieces. And that's a standard assumption in graphical models that so if you remember the reward that I had, it had like fit to the data. And if you look at one piece of it, which is one data point, there's going to be some joint probability that involves that data and some latent variables. And we can break it down, like in graphical models, into smaller pieces corresponding to the statistical dependencies or causal dependencies that exist between variables. So that's the sort of thing we can exploit so that we don't actually need to compute the full reward, but we can get a partial reward for some of the statements actually are consistent with some of the pieces of data, and then you can get a bit of reward and a bit of reward.
Thank you.
When the agent considers different hypotheses to test, how does it go get data to test which hypothesis is true or which one is false?
Well, that's the standard active learning problem, right? It wants to choose experiments that will provide it with the most information, and that information in an information theory sense can be estimated using the model itself, because it's just some marginalization of log probabilities that come from the model itself. So we could have another neural net that estimates how many bits of information we would get by doing an experiment. And it's very close to the way we're doing now active learning with GFlowNets. And then that would drive which experiment would be conducted. Like it would be a reward for deciding what to do And then the GflowNet would sample experiments that have a high information gain.
Also, like, to what extent do you see like methods from goal conditional reinforcement learning?
From what?
Goal conditioned reinforcement learning.
Goal condition, right.
Help in acquiring this data actively?
Yeah, so it's a good question. I think that there are many cases where if we want to do this divide and conquer idea that I was talking about, we want to do something like goal conditioning. Think about how you prove a theorem, right? You might not want to generate directly a full proof, but you first create some sub-goals, which are like lemmas that are easier to prove, right? So I think the goal conditioning literature from RL could be a useful thing in our toolbox for sure.
Also, one broad question, like in the plan that you presented overall, I did not see a lot of RL. Like, why is it so?
No, I repeated many times that I think we can take inspiration from a lot of existing RL, right? But we're not trying to solve the standard RL problems. We're trying to solve a different problem, which would be good for scientific discovery, would be good for safety. And yeah, it's not trying to maximize reward. It's trying to understand how the world works and then use that in a way that takes uncertainty into account.
Yeah, I was more thinking along the lines of whether the agents that you presented have agency in them, or is it just like...
So the AI scientist doesn't have agency, but it needs to model agency, because if it's modeling the effect of actions of some agent, I mean, it needs to be able to do that in order to predict what's going to happen, if something bad is going to happen or what. So you do need that AI scientist to understand agents, but it doesn't need itself to be an agent. Yeah, frontal cortex, right?
Thank you, Yoshua.
Emmanuel, maybe last question.
Fortunately, I'm just hijacking the mic.
Oh, okay. Yeah.
Thank you. Thanks to all the speakers. Thanks to all the organizers. It was took a long time to organize all of this, and it was very fun. So also thanks everyone for coming.